Okay, we are live. Let's get started. Hello, everyone. Thank you for joining today. As some of you probably already know who have joined this speaker series before, this is our guest speaker series that we do every month.
Okay, we are live. Let's get started.
And hang on, let me
Thank you for joining today.
Mute the YouTube stream I have going because that's gonna give an echo. So as some of you know, we do this every month, inviting a guest speaker and discussing like an interesting topic with us. So glad you're all here. And this is one of those activities we found easier to move to a digital format or a virtual format when the pandemic hit. And we are hoping to go back to in-person soon, but this probably will still have a virtual component because we have found out that we are able to reach a lot more people, and also we are able to now get speakers who are outside Bay Area, which is pretty cool. And we have one of those today. So getting into introductions, Pablo Sobron here, he's St. Louis based and joining us from there, and have been doing research on a variety of things. I'll let him go into it, but he's originally from Spain and he did his PhD there, and thankfully for us moved to US, I guess, to do his postdoctorate at first. And that's where he continues his research on working with SETI and NASA, and also I also founded its own startup about 5 years ago. So that's pretty cool. And I'm looking forward to hearing some about that too. Impossible Sensing, as it's, I think that's the logo on the slide. So let's get started. Welcome, everyone.
Yeah, hey, Sukala, and yeah, thanks everybody for taking time out of a Saturday night to talk or learn about Mars. And I wanted to thank the team in San Jose for inviting me to do this. It's part of our job as Mars scientists to really explain to everybody what we're doing on Mars. You being astronomers either by training or by hobby know how expensive it is to get things up to space, and I think it's a pleasure and a privilege for us to really be able to tell our story at events like today. So again, thanks everybody for being here. The things that you're gonna see here today is mostly pictures and figures and animations and really visual explanation of how we get to Mars and how do we do science there. The many more people that I mentioned here are people within my own company, Impossible Sensing, people at the SETI Institute, where I'm also a researcher, and people at NASA, and of course, international partners as well. So just a little disclaimer here. I will go and share some opinions that I have about space and how we do things there, and those are my personal opinions and do not represent necessarily the views of NASA, SETI, or Impossible Sensing at all. So with that, I think we'll have time at the end, I believe, for questions. So unless somebody has any super burning question while I'm talking, I'll be happy to stay after the talk to respond to as many questions as we can get to in time tonight. So Mars. So I don't have to tell you how excited we've been for the past. It's almost been a year. It was February last year, or this year in 21, when we landed on Mars and with the latest mission. And I think if I can make the slides run. Okay, there you go. There may be a little delay here on the video, but my internet is strong enough for this, I believe. But hopefully you can see the animation here. Can you see the animation? Somebody give me a thumbs up.
Yeah, it's looking good.
Okay, good. So Mars obviously has been something that humans have been exploring and looking up at the sky for for many generations, and from being a red dot in the sky that people associated with gods and eventually war and other things, Mars became, over the centuries, back to perhaps 300-400 years ago, object of study by some of the scientists with technology required to really look closer at Mars, zoom in on Mars, so to speak. And with that, we started to discover that Mars had certain features, geological features, that really looked like something that we've seen before here on Earth, right? So things like mountains, perhaps even volcanoes, some craters of impacts, and even canals or certain lines that were evident on the surface, that got people to speculate that perhaps Mars wasn't that different than Earth, and even maybe even hosted Martians, which, and I'm quoting, I think, from a famous astronomer from last century, that perhaps Martians are enjoying tropical weather as we are in places like Florida, with their own beach and ocean out there. So today, obviously, we know that Mars has no oceans or lakes or water on the surface, but we know, based on research, again now coming back closer to this century, with rovers and landers and orbiters now on Mars, we're learning that a few billion years ago, there were bodies of water there, liquid water, because there was an atmosphere that kept equilibrium. So the conditions were such that liquid water could exist. And that's how we explain not only the morphology and geology that we see on Mars today, and perhaps even in these photos that are real photos from orbital data, but also more importantly, explain the geochemistry and the minerals that we see today. So every single mission, every single rover that NASA has landed on Mars in this century, starting with Opportunity, Spirit, and then with Curiosity, and more recently with Perseverance, has found evidence of chemistry and or minerals that can only exist and form when there was water. There was water there to make them, right? To precipitate out or to evaporate out. But whatever the mechanism, it is well established now that Mars once was a place where the conditions were such that life may have emerged. We don't know, and we still don't know as of today, and it will take a while to really answer the question of whether life ever took hold or developed on Mars. But what we know now is that at least the conditions were there that could have supported life. Even today, to take it extreme, even today, there are certain places on Mars underground where we know that there are habitable niches, as we call it, places where the conditions are such in humidity, temperature, and nutrients and water that we know that life could live there, because we have found life on Earth in very similar environments. So, of course, Mars is, and I don't have to explain this to anybody at this point, Mars is the prime destination for NASA and other agencies around the world to look for life, and qualifying life here as life as we know it, so life based on carbon, and life that at any rate we think that could only have been either microbial or bacterial in nature, nothing more developed than that, because the conditions on Mars didn't support that, so would never support that. So when we say we're looking for life, we say we're looking for either life today, so microorganisms that exist today, or microorganisms that existed in the past, but left certain imprints, certain fingerprints, even within the rock, that we can now analyze and trace back to presence of such life. So all of that thinking, that I poorly described in a minute, it's been the subject of study for decades by scientists and technologists all together. And of course, government agencies that are supporting a very complex and very intricate ecosystem of missions that will eventually, inevitably, end with or conduct to human presence of Mars to really take exploration to the next level. Because as we'll see in a few slides, working with rovers and robots is very complicated. It's very slow and very frustrating for those of us who've had the dubious pleasure sometimes of trying to tell robots what to do on Mars. So eventually humans will take over, or at least co-work with robots there to keep answering the question about whether life may or may have not took hold on Mars. So, a couple Mars facts for those of you less familiar with the red planet. So, Mars is about half the size of Earth in diameter. About same order of magnitude. So that's why we look at Mars as a place that is similar to Earth, at least again in the same order of magnitude of size. Because of the size and because of what we know about the rock on Mars, we can calculate the density and we can calculate the mass. So we know that Mars is about 10% of the mass of Earth, and because of that, of course, affects gravity, and which is very important, as you will see when we talk about flying on Mars. But if you are thinking about putting a diet, I think on Mars you'll have a probably easier way to get a good number on the scale because of the third gravity level that we have over there, which again very important for how we explore Mars, as we will see. And essentially one thing that we joke about is we can break all the athletic records that we know on Mars. By jumping higher and perhaps longer as well when we get there. So all this is important together with the temperature. Probably temperature is the key element here. Is that the swing or the range of temperatures that Mars experiences goes from ultra cold, minus 285 Fahrenheit, all the way to super hot for Mars standards, considering how far it is from the sun, of about 90 degrees Fahrenheit. So everywhere in between is your life on Mars. So when you go from winter to summer, this is what you see. When you go from day to night, this is almost what you see as well. So the problem that this brings is that, water couldn't exist in these conditions, especially because there's no atmosphere either. Therefore, any water that goes to the surface will sublimate away very quickly during high temperature. But this really makes exploration of Mars a very complicated ordeal, because we need to make sure that anything that you send to Mars can survive at least these extremes. And if you have ever tried to use your cell phone below water, you know how long the battery lasts, probably about a third of the time that you could use it when it's normal summer day. And things start to not work very well. Electronics, mechanics, systems really don't like cold or hot. They like either or. You can make things for working in either or, but working in both is very complicated. So you'll see why in a little bit. So, and of course, another of the big differences with or the big features of Mars is that it takes twice as long to go around the sun as Earth does, and this on itself, of course, is explained by celestial mechanics. But the practical implications of that is that we can only afford to launch missions to Mars on very specific windows of time, which is when both planets are close to each other. So that only happens every other year. So that's why we don't have so many missions to Mars, and they all launched on the same period of time. Think about the Chinese mission that was launched last summer along with NASA mission in the same month, because that's the window that we had in 2020 to really launch this mission. So you have to basically take the same train, so to speak. So all of these conditions means that it is still, and it will be for a while, complicated to land on Mars successfully. So I think this score is a little outdated, but basically we're about 50% success rate at soft controlled happy landing on Mars of all the tens of times that we tried. So again, just to underscore the Mars is close. Yeah, it's only 6 months trip, only 6. But it's still pretty difficult to get there safely. So it's not a given. So when you think that NASA is amazing and we always land and it always works and everybody's happy, it hasn't always been the case. And today the only reason why we can keep doing it safely is because there is tremendous amount of work by teams over a decade or plus of time to make sure that when showtime arrives, everything works as expected. But still, we will see failures and we'll see crashes because, again, it is hard. So this is a slide that I've been using for the last a few years since we launched 2 summers ago, and kind of tells you the story again that Mars and Earth don't travel at the same time around the sun, and there is only places where you can launch. And on the left bottom, you see that when we launched the mission in 2020, Mars and Earth were close to each other, and that's how we can minimize the amount of fuel and amount of time that it takes to get to Mars. As it is right now, it takes between 6 and 8 months to get to Mars if you launch in the right window. So this video shows what we were expecting to happen on the day that we landed. So after the 6 months, and so this is what we wanted to be on February 18 this year. Full disclaimer: this is exactly what happened. So that's why we have mission now. But this was something that people wanted to believe that it will happen. So first thing is that we need to break the spacecraft somehow from 100,000 miles per hour to 0 in about 7 minutes. So Mars, even if the atmosphere is very thin, it still is enough to really either make you bounce off the planet if you don't hit with the right angle, or you can use it to essentially parachute down like we did successfully. But you have to be very careful on the angle that you come in, otherwise you don't really get there. So we're using now parachute to idle brake, so we're using atmosphere to slow down, much like we do on Earth, and different stages on the descent. The spacecraft releases different modules, and eventually releases a sky crane, which is this device that uses rockets, much like the lunar landers on the Apollo mission, to slowly and controlledly find a safe landing spot.
Pablo, are you still there? We lost you.
Back in the day, we just let it go.
Okay, there you are.
Yeah.
Sorry, we lost your connection in between. Can you hear us? Uh-oh. Can everyone
I'm sorry,
hear
I think I disappeared.
Oh, okay, there you are.
I'm back. Yeah, I'm disappeared. I disappeared from this. Apologies about that. So
Okay,
when did you lose me?
like maybe 1 minute ago.
Okay,
I think the last thing I saw was when you were talking about the landing, and then you said full disclosure. That's how it actually happened. Talking about the thrusters, I think that's where exactly it was.
So nothing crashed. I'm still alive. Everybody's good.
Okay, good.
And, so I hope you can. Yeah. So all good. So eventually, what happened is that we landed safely exactly where we wanted, and hence the mission started. But it was fun to show this video before the landing, because that was the hopeful thinking, and then the landing was a big relief for everybody to really see it happen that way. So what did we land on Mars? We have the most complex spacecraft or robot that we have sent anywhere at this point. It contains a suite of multiple scientific instruments whose job is to find 32 samples of high priority that we will bring back to Earth. So the mission is not finding life, it's not built to find life on Mars. It is built to find these samples that we think may or may not have life, but we believe they may. But we know that we cannot bring the instruments that we need to determine the life, yes, no, unless we bring the sample back to the lab. And this is the fundamental limitation of doing space science, is that the technology you can physically and feasibly build is not the best you can. So there is many labs in the world that are much better than this robot. Unfortunately, they cannot be packed in a small size and a small volume that it takes to really land on Mars like we did. So all that being said, this is a marvel of technology that is right now doing things like zapping lasers on the surface or rocks at distance. So we can look at now the chemistry of the rocks by shooting a laser without having to go there. We can use cameras to really zoom in now and to look at very fine textures, and you'll see some pictures of that, don't worry, on the rock. So we can actually almost feel like we're there with eyes on the rock, like a geologist would be with a loop, looking at the rocks. And now we have a system tool that is able to core to get a sample from the subsurface and seal it in a container that we will bring back to Earth, hopefully this decade, to analyze these samples that I said before with the best labs that we have. And this rover has one extra bonus, several extra bonuses. One of them is this instrument called MOXIE here on the bottom, and this is a demonstration of a technology to extract oxygen from atmospheric CO2. So of course, breaking down CO2 into carbon and oxygen is nothing new. We do it all the time on Earth in industry, but doing it on Mars, it wasn't clear that we could do it because of the temperature, the low pressure, and other problems that we encountered there. So this tool was built to show if we could eventually generate oxygen from the air on Mars to support human exploration. So the success has already been proven. So the instrument works, produces more oxygen than we thought, so that's a good thing. So check the box, and now we can proceed with the science. Now that knowing that maybe in future we can eventually breathe there if everything goes right. This is animation here. Hopefully I don't disappear again with this, but you let me know if I do. So here, because we don't have video assets from the rover on Mars when it's working, it uses all the power to really do the job. So we don't have videos of this what you see here. But what's happening on Mars is exactly what you see in the animation. We have the mast that is rotating. This telescope that you see on the white box on top, that's the laser that shoots and indicates the chemistry and mineralogy of the sample or the rock without having to go there again. And what we're happy with, we'll see, we have this big arm that is able to deploy a couple of instruments there, one called Sherlock, one called Pixel, that tells us more about the surface of the sample in question. And again, when we like it, we deploy this coring tool that you see here and get a core, get a couple of inches, 3 inches actually, long core cylinder of rock that eventually we bring into the rover to do several things. Of course, if you look at the cost of the mission, probably about $4 billion for B, and 32 samples that we're going to bring back. You can do the math and how expensive each of the samples are going to be. So the first thing you want to do is want to make sure that you actually have a sample, right? And you don't have an empty canister. So we have a tool there to measure how much. And if we validate that we have what we want, then we can seal it, much like you seal a can of preserve. And then we store it and cache it so that the next mission to Mars can pick it up and bring it back. So that's how it goes. There is 32 slots, and we've already collected 5 samples, and we move on every time we do a sample. We just go to the next science target. And the idea here is to collect a diversity of targets that gives us confidence that at least one or some of them do have the right chemistry, the right minerals, the right habitats where life may be there. So again, we don't know if there's life there. We will not know until the samples are brought back to Earth. So now going to the real. Okay, so this is now real. No animations. This is a panorama, 360 photo taken from the landing site. So this is the first day of mission, and here really the value of this picture is not much about can we see any cool rock or any cool feature. Not really. I mean, of course, everything's cool on Mars, but the idea here was to really show that hey, we have wheels on the ground. And we have eyes on the ground too that work, and actually you can start, checking the boxes. It took about a month and a half just on testing and commissioning the mission before we can actually do science. So scientists were really excited. So some of them were already digging deeper into the sample, into this, picture. This is a real zoom image of this panorama, where you can start seeing features at a distance. This is probably about 20-25 meters away from the rover and 100 feet. And here we can see rocks that have been carved by the wind over millions of years of a little bit of sand blowing past and really sculpting very interesting features there on the basalts and all the igneous rocks that you see on Mars today. So this was no science, but this is already very exciting for the science team who was really, thinking about what this means for the overall planet. This picture here is another panorama. This one is showing the rim of the crater where we landed. Perseverance is in a place called Gestural Crater. And this crater is very special in that, beyond being pretty sizable, or a few kilometers wide, it does have a delta, a river delta, that connected back in the day, perhaps 2 or 3 billion years ago, with a river that brought in sediment and other dissolved rocks and particles into the crater itself. So the crater was being fed by a river, and we picked this landing site because we know that on Earth, river deltas and all these places where you have body of water carrying nutrients and sediment entering a different body of water, things start to precipitate down. And we know that the organic load of river sediments on Earth is some of the highest in the planet. And we speculated that perhaps if there was trace organics and living matter on Mars flowing in the water systems, some of that may have been sedimented down, precipitated as a clay or a phyllosilicate, and be trapped in the layers and be there for us. So this is where we are right now. And what you see here is the rim of the crater, which if we are successful with the mission A, and B, if we convince NASA to keep giving us money to keep working on the mission for the next 10 years, we will eventually escape the crater and go into the next phase of the mission, which will be exploring, what's above where we are. So this is a photo of the first wheel operation. So the first roving on Mars with this robot, and again another big milestone that showed that the wheels work and we can move around. So this was an important photo, and that's why it's typically in this kind of talks, because it's really makes us very happy to know that now we can move. And again, this was passed in March, but it was still pretty amazing to us that we could deliver this piece of equipment in one piece, and everything is working as expected. So here. This is more recent. This is from September or October, I believe. This is the first core that we collected with the coring system. So here, what you see is the tip of the coring bit. So this is the teeth, right, that chew on the rock and takes us down into the subsurface. And what you see in the middle of the image is the face of the core that is being taken out from the underground. So again, it's about half an inch thick and about 2.5 or 3 inches long core here. And this is an animation of the sequence of images that we took to validate that we indeed had a core here. Because again, we want to make sure that when we seal the can, right, we seal the tube, there is something there for us when we open it back on Earth. So here is the two first cores that we got, two holes that you see on the rock in the arrows. So that's the very first ever drilled cores on Mars that we have taken. So Curiosity, the rover that's been on Mars for 10 years now, does have a drill, but it's an auger. So it's much like the drill you have in your house to drill a hole in the wall. So you get powder out, and that's what you get. You don't get a core. So this is the very first time we are able to get an intact piece of the subsurface. In this case, it's a rock. So we drill on the rock, but eventually we will, and we have already dug into an outcrop that is essentially subsurface of Mars there for us. So in a review now in core of what a beautiful morning looks on Mars, and this is the path that we're taking now. Is a little bit here into this to this formation, this ridge that you see on there. And whenever you see layers on Mars, for those of you who are not geologists, every time you see layers on Earth too as well, that means that different periods of different water activity with different conditions, different chemistry, precipitate different minerals, sandstone, limestone, calcite, clays, and think about the Grand Canyon, all the different layers that you have. Those are different times in history. Same on Mars. There's been many cycles of dry, wet, where we have now exposed in the rock record to look at the past of Mars as we go. So again, more photos here show informations that are interesting in many ways for geologists. I'm not a geologist, so I will not try to butcher the science here. But what we're seeing here is a lot of altered rock. That's what you see, gypsum perhaps, or calcite. That's the bright albedo, the white parts on the rocks, and lots of that have been transported down, moved around by perhaps fluid water moving on the surface. So here there are 4 audio clips here because I like to show this because for the first time we do have microphones on a rover that actually record the sounds of Mars. So so let's listen to it. First one is the wind on Mars. Did you guys hear that? Could you hear that? Okay. So that's what background noise of Mars is for the most part. There's always a little bit of air moving, and even if it's only 10% of the atmosphere, that air is enough air, right, to transport dust and generate sound waves that we are now collecting there. So so one of the instruments that I mentioned earlier, the laser. What it does, it delivers a lot of energy into the rock, and it generates plasma. So the plasma is very hot and it expands, and the shock waves that carries with it, we can hear it as well. So this is what you hear next here, the laser tapping. So you hear this metallic clack, 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 clack. So that's every single pulse of energy shooting at 10 hertz or 20 hertz, maybe. You can count, but it's shooting repeatedly on the rock. And every time we do that, we get a ball of light, plasma, that contains the chemistry of the rock, and that's how we know chemistry of rocks on Mars. The next one is the rover driving. So you're gonna hear what it sounds like driving with an aluminum alloy wheel, 6 of them actually, on very hard basalt rock. Yeah, so that sounds a little scary and sounds like a can banging with a hammer, but that's exactly what it looks like when you really hit hard rock with an aluminum wheel, which is what we're driving on. So that was very interesting to hear, and we're using that to understand the properties of the soil now, or the terrain, by looking at the sounds of the wheels on it. And one of the highlights of the mission in terms of coolness factor, I think, is that we have a helicopter. For the first time, we have a controlled flight on another planet, and this is what it sounds like when you fly on Mars. It's a very faint hum because we're at a distance, so maybe you don't hear, so all these audios are on NASA's website. So if the technology is not helping us today, you can always go there and listen to it. But I promise you, it flies, and you'll see a few pictures here. Anyway, Sounds of Mars, something that now they're all playing together. Okay, yeah. So anyway, this is I'm gonna skip this video because I think it's very heavy, and I don't want this to break the internet again. But here it was a video that Lockheed Martin and JPL made to show how the helicopter is stored on the rover. So it's a little bit too long, so I'm gonna skip it because we're going there. But this is a bit more interesting. This shows what's actually happening on Mars right now, and I think. Again, we didn't know if we could fly on Mars, and the highlight of this demonstration is that, even in a planet with very, maybe we'll play it. So since it's playing now, one of the things that we didn't know is that Mars has only 10% atmosphere. How can you effectively generate lift with a helicopter to be able to push enough air right under you to fly up? So the solution is obvious, right? So you make bigger wingspan, so you make longer blades. So the wingspan of this helicopter that carries a mass of about 150 grams, so much less than the cell phone, it has a 2 meter or 6 feet wingspan because we need to move that much air again to be able to live there. And the other answer to the problem is, you spin your motor faster. So these motors can spin these big blades at about 4,500 RPMs. So you don't think that's much because any DJI drone you can buy now commercially does it faster than that. But moving 2-meter wings at 4,000 RPMs on batteries, that is a feat of technology as well. So what we've proven now, after 15 flights, is that we can fly very well on Mars, despite the challenges there. So this is a real photo taken from the rover of the helicopter hovering at about 5 meters over Mars. This was taken in May this year. This is a animated photo, GIF of essentially a video, right, of the helicopter during the first flight. It was just lift up, rotate, and come down. That was the mission. And after that, it's all been flying farther and farther and longer, and still successfully going. Everybody's very proud of this. And this is an animation of the shadow of the helicopter taken by itself as it's flying horizontally over distance. So you see of course, the frame rate is different than the spin rate, but that's why you see the dual blades rotating at different speed. But this is what's happening on Mars right now. And this is a photo taken on flight 15 about 10 days ago. It's the latest flight that we took, and we're planning now for the next flight, hopefully next week. So if you're curious to see where we are right now, there is a beautiful tool on the Mars 2020 mission website that is called Perseverance Location, and you can play with layers, you can calculate distances, and here you see on the left side that blue, gray, or green area there. That's the shelf, right, of the crater. That's the rim. So eventually we'll drive over there. You'll see a little detour here of the rover. It's not going straight up because there is science targets along the way that we discover as we go, that we decided to spend time there as opposed to driving. So you can follow real time what's happening here. I took this morning, so this is where we are right now. What's going to happen in the future is that this mission in this path that you saw there is taking already 5 or 6 samples. It'll take 25 more if everything goes well over the next 2 years. And eventually it will fill this cache. It's a canister, and it will leave it behind. And it will continue on now without the duty of taking course anymore, just driving around and doing more science, because the rest of the instruments still work, of course. And eventually, together with ESA, the European Space Agency, NASA in the second half of this decade will launch a fetch and retrieve mission. This is the blue segment here that you see on the graphic. That the job will be only to just go find the cache and bring it back to a vehicle that will take it up to orbit, where a third mission will basically fish it and bring it back to Earth. So this is a complicated sequence of missions, not unlike what you saw in The Martian, the movie, where one spacecraft goes up and the other one catches it in mid-flight and brings it back to Earth. So this is the concept for this mission as well. Of course, NASA is not the only agency doing things on Mars. There is the Chinese space agency, landed on Mars on March this year, and this is the first time another country successfully lands a rover on Mars. And they've been working on Mars for as long as NASA has with this rover. Unfortunately, they don't share much details, but we know that the rover is working well, takes pictures, it has a laser that saps rocks as well. And they seem to be very happy over in China with how they're working on Mars. But again, they don't know very much, so I wish I could show you something, but I can't. Europeans, though, we've been busy as well. In 2016, we launched the phase 1 of Exomars mission, which is the orbiter that has been flying around Mars for the last few years, getting data remotely. and finding the sweet spot, the right landing site, so that in 23, when we land the rover that we launch in 22 next summer, this is the Exomars Rover, then we'll, finally Europe hopefully will have a working asset on the surface of Mars that doesn't crash or doesn't stop working suddenly. So this is the Exomars Rover that we launch next summer, and the novelty of this rover and the reason why it's been delayed for about 10 years since the original launch date is that it will have a deep drill, a 2-meter drill, 6 feet deep drill that will allow us for the first time ever reach a depth under the surface of Mars where we know everything that's there is protected from the radiation, the UV exposure, and oxidation from CO2 that everywhere on the surface of Mars and the shallow subsurface suffers. That's why everything's red. So we know that at about 1 meter, 1.5 meters, 2 meters to be safe, we are totally protected from harmful effects of atmosphere and cosmic radiation, which could, and is being proven, that could break down organic molecules, therefore erasing any traces of life that may exist on the very first meter on the surface. This is controversial. There is no yes right answer or no answer. As a matter of fact, as I was explaining for the last half an hour, NASA's mission only drills 3 inches. Yet at NASA, we think that in some cases, that should be enough protection for some biosignatures, some traces of life to be present, that we can detect them back when we bring these things back to Earth. But the Europeans, and I'm part of the mission too, so I'll speak for us and us, we also think that to be safe, why not drill deeper? So the mission is going to be taking samples from 2 meters down, and as opposed to getting the sample back to Earth, in this case, we're sending there a laboratory internal to the rover that contains some of the most sophisticated in situ geochemical tools to really try and do our best. Again, we're not going to be able to find present life. We will be able to find fossils or traces of life from the past with this rover. So that's the bet of the European Space Agency, and everybody's very excited to see how this complements the findings of Mars 2020 mission today. So in all of this, this is a nice cartoon that I guess shows the aspirational future of missions to Mars, and it's again, we need the samples back here. There's no way around that to do the best science on Mars, we have taken the path of doing the best to get the best sample, but bring it back to Earth where we have the best scientists and the best technologies to analyze the rocks. And eventually, of course, another aspirational / inspirational thought of building or bringing habitats and an infrastructure that humans require to support inhabitation of the red planet. In the beginning, of course, temporarily, exploration purposes, and just because we're humans and we like to go there. But eventually, Mars as a colony or outpost of humans is something that is not far to imagine right now, especially given how things are shaping up in the space environment right now with private partners coming into the game as well. And just the last slide here, just because we talk about Mars a lot, and it's been a great year, and it will be an amazing decade for Mars science with all the rovers there. But one thing to not forget is that most of the exploration that will happen on Mars in this decade and the next decade and beyond is gonna be enabled and requires actually exploring the moon. And this is so because it's way cheaper and it's way less risky to demonstrate technologies, to test new ideas, to practice with humans on the moon, of course, than it is on Mars. We've done it on the moon. We know how to land. We know how to keep people alive there. And we know how to bring them back safe, more importantly. And I think, as you know now, with the Artemis program, with all the commercial players thinking about the moon as a place to develop resources, perhaps even build rockets, get fuel on the moon, so we can launch from the moon and not from Earth, with all the cost savings that brings. The moon is really the gateway to Mars. So stay tuned for moon activity. NASA is going to start flying missions to the moon pretty frequently now, at least robots in the beginning. And perhaps as early as 24, 25, NASA will land the first woman on the moon and the next man on the moon as well, to really start to develop human presence on there, to enable, again, gateway effects coming from the moon and elsewhere. So I will leave it here, and I'll take questions that you have. Thanks so much for listening.
That was great. Thank you so much. We overcame the technical difficulties and and it all worked out. But I'm getting some questions here. So Nick is saying, amazing, thank you. Stefano, thank you, Dr. Sobron, for a really interesting presentation. I have a question about life on Mars. How can we be sure, sending robots and rovers from Earth to Mars, aren't we the ones bringing microbiological life to the red planet involuntarily, using our artifacts as vessels?
That's, that question keeps about 200 people awake at night every day at NASA. So there is an office at NASA called the Planetary Protection Office, and the job of that office is to guarantee that we clean the spacecraft to the best of our ability. Things we do is we bake everything at about, but depends on the mission, but we bake things hotter than what you could use in your own kitchen for about a few days or weeks at a time. We shine ultraviolet light everywhere. Sometimes we inject cleaning products, most like Lysol, to really remove as much bacteria and microorganisms as we can.
Okay.
But although it's true that we never clean everything to perfection, because bacteria are pretty smart at hiding in corners. But this is something that we take very seriously. And as the question said very rightfully so, it will be a shame to find life on Mars only to discover that it's life that we brought back to from Earth. Right. But there is also a more philosophical reason to really try to avoid that. We call it forward contamination. Is that what if there is an ecosystem on Mars? We bring our own life, and our own life kills that ecosystem or destroys it, therefore committing space genocide of sorts. So that would be another tragedy that we don't want to be part of, right? So so I think this is a thing that agencies are very concerned about, and a lot of money and time and effort is spent in complying with planetary protection policies.
Cool. Any other questions? Okay. So I have a question about and it's I won't phrase it as a political question, but like now that we are starting to go to Mars, how are different countries sharing the responsibility of doing their research in a sustainable manner and not disrupting the environment? Has there been any discussion around that, and have they established some kind of treaty, even if it's not really own land or whatever?
Yeah, no. So that's a great question. So yeah, there is a space treaty. inspired by the Antarctica Treaty that that all countries have signed, and it says something in the lines that nobody owns any place in space. You cannot claim, a parcel on the moon or Mars, even if there is people there selling plots of land on those planets. That doesn't carry any weight because countries legally are bound to this treaty that says that this is, is humankind's asset. But to ensure that this is kept, there has been, for the last 20 years actually, there has been a few universities that are offering a degree in space law. And space law, of course, most of the applications have to do with low Earth orbit, satellites and applications near Earth. But a lot of the time is spent as well in discussing issues like the ones you bring up here. For now, space is ruled by maritime law, so that's the blueprint for that. But it will change, and we don't know how it's going to change and shape. But as more commercial players are coming into the game, that's going to change very quickly. So yeah, I think at the scientists, of course, are a different beast, and they're all working together to make sure that information is shared and data is common to everybody. I think it's going to be a more political ordeal to make sure that things get done properly. But we're working on it. So that's
makes sense.
It's promising. It's promising.
Let me check the YouTube channel real quick if there are any questions in there. No, I don't see any in here. Stefano has another question. Why so much interest to visit and maybe later colonize Mars when Moon is much closer? What is the difference? The atmosphere, even if so rare, or the possible presence of water?
Well, actually, the Moon has a lot of water trapped either in minerals or also in cold traps. There may be chunks of water there, but that's a different topic. But so the issue with Mars is very much comes to the way humans look back at our history and our past, and there's a reason why we go to places that are hard and difficult, and it's exactly because they're hard and difficult to get to, and we just need to go because we need to go, and it's our nature to really go and settle new places and develop civilization over there. Something that we've been done for as long as we've been humans, and we will keep doing that because that's in our genes. But there is a more selfish reason to do that, and is that we do know that eventually the Earth will stop being inhabitable, either by our own doing, or by the sun blowing up, and eventually going dark. So it is in our nature to preserve the species. Therefore, although none of us will live on Mars permanently, I don't think, and much less leave the solar system, that will happen. So think about this as the baby steps on humans' expansion. Solar system, eventually galaxy, and eventually intergalactic species. Maybe like we've seen in the movies, maybe not, who knows, but it's just part of how humans are wired. So that's why.
Cool. Let's see, any other questions? I'm not seeing any in here. Let me check.
I think I saw one about DNA somewhere. I don't know if.
I don't think it was a question. I think she was commenting on the discussion around how we make sure we don't pollute the biological trace on or bring life involuntarily. I think the comment is that just like we can precisely trace back DNA sequential changes, we'll be able to tell what's ours and what's ancient Mars. So
and that's why we probably will not be able to fly DNA sequencers to Mars that are accurate enough for the next. This is crystal ball thinking, but probably for the next 10-15 years we will not be able to have technology that is ready to do that on Mars. So that's why we're bringing things back to Earth. Yeah, exactly.
Wow. Okay, that's interesting. Well, I think that's all the questions we Oh, what are areas of research in your field? Is what Philip wants to know.
So the whole. I'm gonna give you an example on this mission in particular. So in the field of exploring Mars, we need biologists, chemists, physicists, engineers of all trades, artists, to make the cool graphics that you see. There is hardly a field of STEM, and now perhaps also the arts, of course, that is not needed or required to enable space research.
Right.
And the more complex things we want to do, the more we need to go out and find skills in many other fields. So whatever you're studying these days, even law, space law, it's it's something that is needed today, and it will be more needed as we keep moving forward.
Right. Okay. Cool. What countries are competing to make manned missions to Mars, and how are they doing? Well,
so
the question is from Kanchan. I'm assuming that's what he meant, but it's spelled as area, so I'm assuming he means like how are they doing?
I was trying to type as fast as
yeah. Okay. Thanks, Kanchan.
Yeah. So the answer is no. There is no competition because we don't even know how to do it yet. So what I know is that NASA is investing in this. So the US, any mission that the US launches, NASA typically carries Canadian Space Agency and European Space Agency contributions. So at the very least, these three agencies are already thinking about that, and are the only ones that are investing money at the rate that I believe is needed to really push this forward faster. Now, the reason why nobody else is doing it, again, is because we have no clue the risks yet. We know some risks, of course, radiation, but there is the psychological risks of sending a mission to Mars that is going to last 2 years, perhaps, maybe more, and having 5-6 people confined into a space the size of this room, maybe. That's almost like it's more psychology than it is engineering at this point. So it's really, the point is that very few, and I'm sure China is thinking about this in some capacity, but again, not much disclosure there. So, but realistically, forget about any Big Brother type private venture that like Mars One, I think is the name of that. So that's not going to happen.
Jeff Bezos is still not planning to go to Mars yet. So Jeff Bezos and Elon Musk are
no. But what's going to happen is that again, this is personal opinion. Is that there's no way NASA can afford to do that on their own. NASA's budget is, it's $20 billion a year, give or take.
Got it.
Seems like a lot, but it's not a lot to do the things that NASA does. So we're pretty cash strapped. So we're going to have to find a way to get commercial partners interested into this. And I think, and you hear Elon Musk and others, they do want to do that. Right. But also they're not going to foot the bill alone, right? So I think the trick is going to be to find a value proposition for both government and private that brings value to all partners. Right. And that combination is the only way to get there. So it's up for grabs. When is that going to happen? I think the technology barriers are such that nobody can credibly say that we will land humans on Mars in this decade. But everything indicates that the 30s is the decade of the 2030s is when humans land on Mars, but it's not a private and public combination.
I see. Cool. Let's check YouTube one more time. No questions there. Philip is asking, how can we help? What is your organization? I think even I would love to hear a little bit about your sensing startup.
Yeah, Philip, without knowing what you do is difficult to really, but tell you what, maybe what I tell you now help you. So I used to work, I work at ESA up in Europe. That's when I was doing my PhD. I work at the Canadian Space Agency. I did work for NASA for a minute. And then I realized that, I wanted to do things a little faster and with a little less bureaucracy than government. And having tested the waters of being a government, I know how hard it is from the inside. So I thought that I had enough skills and enough good ideas that maybe I could start a company and get things done faster and also make some money. And the genesis of the company was exactly that. And I was in the Bay Area. I wasn't very far from where you are right now, down in Mountain View. And I started the company. I moved back to St. Louis, where I first studied in the US as a postdoc because of essentially cost of living. If you're a startup person, cash is something that you typically don't have from the beginning. So paying rent and paying salaries in the Bay is a little difficult. But so anyway, what the company does now is we are building optical sensors to help NASA find life on Mars. So I personally was part of the 4 teams that build laser technologies that are now on Mars or will be next year with Exomars.
Right.
So I bring all that baggage now to the private sector. So I can iterate faster on these designs now as a small company, agile, and more risk loving. And right now we're building the next generation of sensors for NASA to go find life on Mars, on Europa eventually, on the clouds of Venus maybe, but more immediately we're building optical sensors now to go and explore the moon, go finding water on the moon, go finding the resources that we need to generate fuel for rockets, and eventually materials to utilize to build structures on the moon. Metals and other compounds. So of course we're doing all that funded by NASA mostly. To be able to keep doing things faster and making money so we can actually accelerate our space research. The second part of our mission at Impossible Sensing is to really turn all these innovations that we build for space, turn them into solutions to reverse climate change on Earth here. So, all these things that make space instruments being so special, very small, very rugged, they're very low power consumption, very intelligent, because you cannot talk to them every day. They have them to make their own decisions. So all of that turns out that is what we need on Earth to monitor indicators of global change, emissions, glaciers retreating, soil carbon, things of that nature. We're now using our technologies to enable farmers, for example, to monitor carbon sequestration when they use better farming practices. We're using this in oil and gas production facilities to replace massive systems with valves and pipes that leak methane all the time. We're taking that out of the picture now by bringing smart, compact sensors that don't leak to the atmosphere. So, that's the things that we do is essentially we make the impossible possible. That's kind of the tagline, and it's really true. I mean, we really taking the breakthrough technologies that we need in space. We're now turning back into solutions for Earth that help everybody every day. So that's what we do in a nutshell. Hopefully that clarifies that, Philip.
Cool.
Yeah.
So,
but
sorry, go ahead.
Go ahead. No, I was saying that just to finish, because I mentioned SETI Institute earlier, and most of you probably know that the SETI Institute is based in Mountain View, next to you.
Yep.
So there, I'm a scientist there, and at SETI Institute, we do more than just looking for ET signals, like Jodie Foster did in Contact. Although that was the origin of the institute, but at SETI, there is a team of people that is looking at habitability of Mars and other planets.
Right.
Answer to be able to answer the even more fundamental question of, are we alone in the universe? So between SETI and NASA Ames down there in Mountain View as well, you guys have a cluster of world-class research in astrobiology, and I invite you to reach out to them and go visit. There's public spaces to learn a bit more about what it takes to really apply the best brains that are working there right now into these questions about, are we alone? Is there life elsewhere, and where? And how do we find it, right? So you guys have that there down the road. So I would take advantage of that if you can.
Definitely a difficult question to answer. I actually skipped past one question that Manoj asked. Have private companies like SpaceX ratified the space treaty, since enforcement of any such treaty across the vastness of space will be hard?
No, as far as I know, they have not. The treaty is government level, but SpaceX being a US company, it is bound to abide by the law of the land.
Okay, that's good.
So by definition, they should abide. Now, to the second part of your question, how do you enforce that?
Yep.
That's the $1 million question, right? And I think that's where the space law field is developing into a way to, guarantee that all humankind benefits from space, not just, a couple companies. And that, we do the right things in space based on lessons learned on the things that we've done wrong on Earth. One of the things that I really love about working in this business is that I haven't seen this anywhere in other fields, in industry or academia or any other field of research, for that matter. Is the level of collaboration and transnational flow of information, insight, and work that happens in space. And an example of that is NASA as an agency of government. NASA is not shy of hiring foreigners, case in point, to help the mission, because all that matters is, can you help the mission? Do you have what it takes to help us? No matter who you are, where you're from, doesn't really matter. There's a job for you here. And I think, things like the International Space Station, is a contribution of all countries. I think it's the largest and most vast international example of how countries can work together to really further humankind. And I think space, because it's such an inspiration for most of us, is something that really humbles you and humbles everybody. I think that's what's kind of creating this great culture and great atmosphere where countries do work together for the most part. So I think that enforcement,
that's the key.
My hopeful thinking is maybe this enforcement will come from the stakeholders themselves, right? So
of course. Well, I think that's all the questions we have. Oh, there's one more comment in chat. Oh, one more question. Manoj again. I work in machine learning. How is it being used for your projects, and how can we help the ML community? That is.
Yeah, it's a great question, Manoj. So machine learning is at the epicenter of everything we do here. I'm not talking just for my company and my colleagues. I think as we develop, as we require more capabilities to explore, we require more autonomy, more intelligence. We require essentially robots to not call home every day and sending us terabytes of telemetry data, bits and bytes. No, we require robots to send us the insights, the knowledge that matters to us, right? Is there life? Yes, no, that's it. Perhaps that's all you need to send, right? So, here is where machine learning and other applications of computation are quintessential to really enable the next phase of space exploration. Is because we need to get humans out of the loop. We need to let the robots work on their own efficiently, effectively, to work for us and deliver the answers that we want. And I think, how can we help? I mean, you are already. There is, if you look at the SETI Institute website, there is a program called FDL, is the Frontiers Development Lab. And what this is a summer program where teams of students, postdocs, and early career professionals gather together, sponsored by players in high-end computing like NVIDIA, IBM, and others. That is actually pushing the boundaries of deep learning and other disciplines like machine learning to really help answer fundamental problems by using computation. So this is very, very well understood now in our field that we cannot progress fast enough without the use of machine learning. So yeah, I mean, this is actually very hot topic now. So Google that. I think you'll see all kinds of applications that are needed there, and NASA has all kinds of now programs to fund and to actually enable research in small companies and institutes and universities to really advance that for the space program. Yeah.
Cool. Let's see, any other questions? Oh, and he's asking how he can reach you. I can, Manoj, you can message me and I can probably pass on your email address if that's okay. Or you can type it in the chat fine. And that way he has it. I mean, if that works.
Yeah, I'll put it here, and otherwise, I'm typing it here. So otherwise, you can always find me on LinkedIn. All right. So shoot me an email, Manoj, if you have any particular question, and I'll be happy to answer. Maybe not tonight because it's almost midnight here. But,
yeah, I know, St. Louis, right? Like it's a different time zone. Yeah. So I guess on that note, we'll probably let you go because it's getting late. But thank you so much for joining us tonight, and thank you for everyone who attended. Now you have his information if you want to ask him more questions. Reach out offline, I guess, and see you again at the next event. Thank you.